What do I mean by equilibrium? What do I mean by dynamic equilibrium? Well, a dynamic equilibrium is defined as a state in which no change occurs because there are two opposite processes occurring at the same rate. So what we can see in the picture here is we've got an equation that we would normally look at as, reactants to products. We still treat it that way. We still treat it as reactants on the left and products on the right. But what's special about this equation is this arrow right here. This is what I call your equilibrium arrows. Notice it's a half arrow one way and a half arrow the other. That means that the reaction actually goes forward and reverse direction. It can go either direction, meaning 1 mole of H2 gas can react with 1 mole of I2 gas to produce 2 moles of HI gas, or 2 moles of HI gas can collide to form 1 mole of H2 gas and 1 mole of I2 gas. The way I've written the reaction is that the H2 and I2 react to produce the HI, but I could write the reaction the other direction as well. I could write 2HI gas in equilibrium with H2 gas plus I2 gas. Now, I don't do that to confuse you guys. I do that just to make it clear that equilibrium means that it goes either direction. But the direction we've written the reaction, we're treating it as reactants to products every time. And we're going to have a constant or a temperature-dependent value called a reaction quotient that helps us determine how far or what extent the reaction has proceeded to, meaning how much H2 do I have, how much I2 do I have, and how much HI do I have when I've reached that steady state or that equilibrium. So, again, no change because there are two opposite processes occurring at the same rate. Let's say I have a building. Say I have a store. And let's say the store can only have 50 people in it at any given time. Let's say you arrive, and because of employees and people, there's already 50 people inside, but there's 2 people waiting outside to go inside. These 2 people can't go inside yet. They have to wait for 2 people to leave before they can enter the store because of the capacity of the store. Now you come along, and you have to wait for those 2 people as well. So first, 2 people leave, 2 different people leave, and these 2 people enter the store. Now a third person leaves, and you are able to enter the store. The number of people in the store has not changed. The number of people in the store has been 50 people the entire time between customers and employees. But the individual people that were there did change. These are all different people, right? Maybe this one, purple, pink, just making their heads different colors so to emphasize that they're different, right? Maybe this one, just making it look different, just emphasizing these are all different people. So different people are in the store at a given period in time. But from a bird's eye view, all we see from the top, if we don't zoom in real close to the store, is, so say we just look at it from, really, really far away, all we see is that there's 50 people in the store. I say constant because we know that the number is changing and fluctuating a little bit, but overall, there's 50 people. That's a dynamic equilibrium. There's no change because 2 opposite processes are occurring at the same rate. The people leaving the store equal to the people entering the store at the same rate. So this is what it would look like graphically. We've got time versus concentration. And we're looking at the reaction listed above. We've got H2 gas, I2 gas, and HI gas. The little brackets here, remember bracket means molarity. So if I write H2 like this means concentration. And we use it to represent molarity because there are different types of concentration or different values we can measure concentration with. So I can see what we talked about before with the kinetics chapter. We were talking about kinetics deals with this. It deals with the rate of change. Now we're talking about once we've reached that equilibrium, that steady state, what is our concentration now? And that's what we're going to deal with over here, the dynamic equilibrium. So no surprise, if I mix H2 and I2 together to form HI, some of that concentration of H2 will decrease. Some of that concentration of I2 will decrease. The concentration of HI will increase because I didn't have any to start. But eventually we're going to reach a dynamic equilibrium where all three species are present in the system. So, two characteristics of chemical equilibria. And again, equilibria and equilibrium. Equilibrium is the singular form, equilibria means plural form. There's two opposing changes or processes occurring at the same rate. So, the Haber process. We've talked about this in class before. 1 mole of N2 gas reacts with 3 moles of H2 gas to produce 2 moles of NH3 gas. That is one direction. This reaction is in equilibrium, though. It can go either direction. I could also say 2 moles of NH3 gas will react to produce 1 mole of N2 gas and 3 moles of H2 gas. The process is in equilibrium. It is reversible. What I normally, now that we're through equilibrium, what I would say, N2 gas plus 3H2 gas is in equilibrium. So again, equilibrium arrows. With 2 moles of NH3 gas. At equilibrium, the concentrations of the reactants and products do not change with time. The individual molecules are still reacting, yes, but at the same rate in the forward and reverse directions. So how do we talk about this? So we have these two, we have more than two, but we have a constant, more than two subscripts. We have a constant, equilibrium constant, that we're going to use. An equilibrium constant is a measure of how much product or how much reactant do I have at some point in the reaction. Specifically, once I've reached equilibrium. The C and the P, the subscripts, we have many of those. They describe the type of equilibrium we have. So again, equilibrium constant is the concentration. It's a measure of reaction extent. So a measure of how much product I have to how much reactant I have once I've reached equilibrium. The reason I say measure of and not specify what type of measure is the subscript tells me that. This tells me concentration, which we mean molarity here. This means pressure. I'm also going to see Ka, which is for acids. Kb is base. Ksp is slightly soluble salts. There's lots of different subscripts we can use to describe different types of equilibria. But for the reaction, A moles of A reacting with B moles of B, producing C moles of C and D moles of D, my Kc expression is as follows. The concentration of C raised to the number of moles times the concentration of D raised to D number of moles divided by concentration of A raised to A number of moles times concentration of B raised to B number of moles. It is products over reactants raised to their coefficients. And notice the values are multiplied here, not added. So don't add them together. Please multiply them. Kc, the C stands for concentration of X. What is X? Whatever you're looking for. The concentration of X in moles per liter. You may also see this written as KEQ, depending which textbook you're using. KEQ still means concentration of X, but the EQ just stands for equilibrium. Your book just uses Kc, so that's what we're going to use in class. We can also have Kp. Kp is the pressure in atmospheres. It's the partial pressure of each species. But same setup, the partial pressure of C raised to C moles times the partial pressure of D raised to D moles divided by the partial pressure of A raised to A moles times the partial pressure of B raised to B moles. The equation overall is called your Kc equation, equilibrium constant expression, equilibrium constant equation. I will most often say calculate your equilibrium constant. Law of mass action. These are all different words you're going to hear describe this equation. We can also derive the equation. If you need the derivation, come see me and I'll talk you through the derivation. But Kp through Kc. To calculate Kp from Kc, we take Kc, multiply it by RT, R being your gas constant. Now, if I want to flip between Kp and Kc, I can do that as well. The big thing here is your gas constant here. You're going to use your 0.08206 liter atmosphere per mole K. Value for your gas constant. T is your temperature in Kelvin. And change in N is the change in number of moles of gas molecules specifically. And specifically final minus initial. So number of moles of gas final minus number of moles of gas initial. Meaning that, yes, it can be a negative value, it could be equal to 0, or it could be a positive value. We also have a reaction quotient, or QC. QC is very, very similar to Kc. The only difference between QC and Kc is at any point in a reaction. It is how much product do I have to how much reactant do I have at any given point, whereas Kc is only at equilibrium. So if the reaction is not at equilibrium, we use the same equation, but we calculate QC, or your reaction quotient, instead of your equilibrium constant. So again, for A moles of A plus B moles of B, giving me C moles of C and D moles of D, I see it's calculated the exact same way. Concentration of C raised to C moles times concentration of D raised to D moles divided by concentration of A raised to A moles times concentration of B raised to B moles. But we can use QC to determine the extent of the reaction. We can use QC to say, okay, the reaction has reached equilibrium, or I need to make more product to reach equilibrium, or I have too much product, I need to move in the reverse direction, and I need to make more reactant to reach equilibrium. If QC is greater than Kc, if QC is less than Kc, the forward reaction predominates. So if QC is over here, less than Kc, it's going to move forward. Forward reaction means produce product. To reach equilibrium. It will continue until it reaches equilibrium. If QC is equal to Kc, the system is at equilibrium. It's not going to change. We've reached our equilibrium. If QC is greater than Kc, the reverse reaction predominates, meaning reactants will be produced. Think about it like on a number line. QC is always trying to reach Kc. So if QC is less than Kc, it needs to go in the forward direction. Excuse me, it needs to go in the forward direction to reach Kc. If QC is bigger than Kc, it needs to go in the reverse direction to reach Kc. If QC has reached Kc already, if it's equal to Kc, it's already at equilibrium, it's at its happy steady state, there's no reason for it to change. And the magnitude, how important is Kc? What is Kc telling us? Truthfully, Kc equal to 1 means true equilibrium. Because, you got your products over reactants. Well, if I'm equal to 1, that means I've got half the products, half the reactants. I'm in equilibrium, right? But its real world application is if Kc is very large, meaning Kc greater than 10 to the third, it's mostly products at the equilibrium. If QC is very small, less than 10 to the negative third, it's mostly reactants at equilibrium. And so we say that this reaction is product favored. Or not even product favored, it's just mostly products. We could say product, we could say goes to completion. For the most part. We can say, since it's so much reactant, it's no reaction. The truth is that every reaction is an equilibrium reaction if you think about it on a spectrum. If you think about a spectrum and think Kc equal to 1 is in the middle, it's where your true equilibrium lies. Eventually, we make so much product, the Kc value is so big product favored, we have no to little reactant. So we just say that the reaction's been completed. We could say, what if Kc is very small? In this case, we have, this is reactant favored. And we have no to little product. We just say the reaction doesn't go forward as designed. There's no reaction. But truthfully, we can treat every reaction as in equilibrium. So Kc is describing the extent of the reaction. How much will this reaction proceed, as written? And appreciable, so it gives an appreciable amount. Appreciable means measurable, observable amount. So an appreciable amount of product is formed. That means that Kc is, we've got actual product being formed. That's an observable or measurable amount, not such a small amount that we can't actually measure it, or that it's basically negligible. Can we look at a picture though and tell, is Kc large or small? Again, Kc is a measure of how much product do I have to reactant I started with. So in the first picture here, I've got N2 gas plus O2 gas giving me 2 moles of NO gas. I see that the N2 is represented by the little light blue balls, the O2 is represented by the little red balls, and the NO is represented by the blue-red ball. So I'm looking at products over reactants. I've got 1, 2, 3, 4, 5, 6 N2 gases. I've got 1, 2, 3, 4 O2s and only 2 NOs. Just looking at this, I should be able to say Kc is small. I don't have very much product. I have a ton of reactant. The Kc value here will be small. If you want to do it numerically, pretend that assume you have a 1 liter container. Assume each particle represents, a mole of particles, and you can calculate it. You would have 2 moles in a 1 liter container, so 2 molar. You could do it by pressure or concentration. 2 squared for the NO times, or divided by 6 times 4 for the O2. I'm going to get 4 divided by 24, pretty small number. H2Br2. Here's my H2, I have 1 of them. Br2, I have 1 of them. HBr, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Lots of product formed here. Again, if you want to do this numerically, assume that you have 1 liter container. Assume each ball represents 1 mole of particles. That would be 9 squared, because again, if I have 9 moles divided by 1 liter, it's 9 molar for HBr. 9 squared, 1 times 1 for the H2 and Br2. That is going to be Kc that is very large.